Recall this SN1 reaction from section 7.5. Remember that if you have a tertiary alcohol, you can actually make it undergo an SN1 reaction in the presence of acid, whereby you convert the OH to a good living group, and then you can now convert that to the corresponding alkyl bromide. Now that's for tertiary alcohols. Now for primary and secondary alcohols, we know that they could also undergo SN2. See, for instance, if you start out with an alcohol with the appropriate acid, you could have an SN2 happening, considering that this is a moderate nucleophile. It's a moderate nucleophile. Okay. Now the SN2 reactions also occur in the presence of zinc chloride as the reagent. If you recall the Lucas reagent, if you remember the Lucas reagent, it's a combination of the alcohol and zinc chloride in the presence of hydrochloric acid. So the purpose of the zinc here is that the zinc is acting as the Lewis acid. So this is the Lewis acid, and so it's able to accept the electron density, and then that now activates the OH as a good living group, and so that now permits the attack of the moderate chloride nucleophile to yield the primary alkyl halide. Okay. Now, if you recall that from section 7.8, that OH group can be converted into a better living group, such as the tosyl, and basically all you need to do is use tosyl chloride in presence of pyridine, and you get the conversion of the OH to the good living group, the tosyl group. Okay, and then that can now undergo an SN2 reaction to yield the completely inverted configuration about the stereocenter. Now, thionyl chloride can also be used to convert an alcohol to alkyl chloride, but this works strictly for primary and secondary alcohols. This is strictly for primary and secondary alcohols. Okay, it will not work for tertiary. This will not work for tertiary, so remember that. And so basically what is happening here is that the OH is converted to a good living group. As you can see the mechanism here, right? And then you can see that the base comes and plucks up this proton, and that yields to this, right? And eventually the reaction is promoted by the fact that one of the products, which is sulfur dioxide, leaves the reaction mixture and drives the equilibrium to the product side. So I want you to note the role of the base, right? What the base is doing here is abstracting this proton right here. So I want you to note that. You can also use phosphorus tribromide to convert a primary or a secondary. Again, this works for primary and secondary alcohols only. It doesn't work for tertiary. So again, you're converting the OH to a good living group, and then the attack of the bromide to yield the alkyl bromide and the formation of the acid. Note that the last step of of using thionyl chloride or phosphorus tribromide are all SN2 mechanisms. Okay, so make sure you make a note of that. And I've done this just to save time. If they fill in the necessary reagents, you can see here that the OH has been converted to a tosyl. See, a tosyl group. And basically how you did that was with tosyl chloride and pyridine. See, notice that there's retention of configuration. It doesn't affect the nature of this of the stereocenter, right? And then you can now make this react with something else, you know, and do something else, whatever. You can now make it react with a nucleophile. A nucleophile can now come and attack, and it can lead to complete inversion of configuration. Can lead to complete inversion of configuration. All right. Okay. Don't forget, this is a negative charge on the nucleophile. All right. Now, with SOCl2, you can also do the same again with pyridine, right? Use SN2 again. Again, you can see this inversion of configuration. Okay, so make a note of that. And you can see that this is a secondary alcohol, right? And this is a secondary alcohol as well. Okay, so these are things you want to make a note of. Now, in section 8.9, we saw that an acid like sulfuric acid, which has a non-nucleophilic conjugate base. This is non-nucleophilic. This is non-nucleophilic. Okay, this is non-nucleophilic, and so it will not participate. It won't be involved. It won't pass as a nucleophile. So we saw that you can promote an E1 reaction because this will facilitate the formation of a tertiary carbocation, which of course can now lead to an E1. Why is the E2 unlikely? With E2, remember, you always need a strong base. Okay, you need a strong base for an E2 to happen. Recall that the reaction generally produces the more substituted alkene. So it involves a carbocation intermediate, you see. Because it involves a carbocation intermediate, it always produces the more substituted alkene. Because if you recall, this will go through this kind of intermediate. This will go through this kind of intermediate. Yeah. Okay. All right. Which will lead to these products. All right. Now, if the alcohol is converted to a better leaving group, then a strong base can be used to promote the E2. And that's basically what is happening here. You see? You have a strong base, and you have a good leaving group. So that will go E2. Now, E2 reactions do not involve rearrangements, of course, because they are concerted. They don't involve a carbocation intermediate. Now, when applicable, E2 reactions also produce the more substituted product, provided the leaving group and the proton being abstracted are anti-periplanar with respect to one another. This is something we looked at in chapter 8 when we're looking at elimination reactions. So you want to go and revisit your notes. We saw how alcohols can be formed by the reduction of a carbonyl, right? The reverse process is also possible with the right reagents. As you can see here, the oxidation number of this is 0. Okay, you have 1, 2, 3, 4. While here the oxidation number is +2. So you can see this is an oxidation, while in the reverse is a reduction. Now, oxidation of primary alcohols proceed to an aldehyde, and subsequently to the carboxylic acid. Very few oxidizing agents will stop at the aldehyde. If you want to stop at the aldehyde, then you will have to use something like this, which is pyridinium chlorochromate. Pyridinium chlorochromate. See, you have to use something like this, pyridinium chlorochromate, right? Oxidation of secondary alcohols produce the ketone. Very few agents are capable of oxidizing ketones, right? You have a secondary alcohol to a ketone, and that the oxidizing agent in this case can be your Jones reagent, which is potassium dichromate in the presence of sulfuric acid, or you can actually use PCC. PCC will also work in methylene chloride. Okay. Now, Tertiary alcohols do not undergo oxidation, of course, because they don't have, if you look at the mechanism, you need a proton. You need a proton which needs to be abstracted. You don't have a proton here. You don't have an alpha proton, no alpha proton. Okay, you don't have no alpha proton, and as a result, the reaction doesn't go in that direction. Okay, the two main methods to produce the most common oxidizing agents. You can use chromium 3 oxide, or this is chromium 6 oxide in the presence of acid and acetone, and you can get chromic acid, or you can start out with sodium or potassium dichromate to give in the presence of sulfuric acid. This, remember, is the Jones oxidation. Okay, this is Jones oxidation, don't forget that. Now, when chromic acid reacts with an alcohol, there are two main steps. First is more like a dehydration. You can see the loss of water, and that leads to the formation of the chromate ester. You can see here that this looks like an ester. If you look at this, ignore the others, but this looks like an ester. So it looks like it's called the chromate ester, and of course the loss of water. That's the very first step. And then the second step, the water comes back in the form of an E2 type reaction and abstracts this proton. So you see, for it to undergo oxidation, there has to be an alpha proton. It has to be an alpha proton. If there is no alpha proton, then this will not happen. See, and that's why you can have oxidation for tertiary alcohols to the corresponding carboxylic acid. See, now chromic acid will generally oxidize the primary to a carboxylic acid. It doesn't stop at the aldehyde. But if you want to stop at the aldehyde, you have to use something like pyridinium chlorochromic, like I mentioned to you earlier. This will stop at the aldehyde. It won't go any further, because you can see here, because of the electron donating effect of this base, the strength of the oxidizing agent has been weakened or poisoned, just like we had in the case of Lindlar's catalyst, in which the strength of the catalyst was actually poisoned. Now, oxidation of alcohols, pyridinium chlorochromic is generally used with methylene chloride, and you can oxidize the primary alcohol to the aldehyde, or you can oxidize the secondary alcohol to the ketone. See, these are things that you need to remember. And of course, if we're going to predict the product for the following reaction, we know that this is a secondary alcohol, so it will be oxidized to the ketone, right? It will be oxidized to the ketone, right? While this is a primary alcohol, and it will be oxidized to the carboxylic acid. Now, also note the fact that because you have an aldehyde here, okay, the aldehyde will also be oxidized to the carboxylic acid. Okay, so this is pretty harsh. See, this is pretty harsh. It's a pretty harsh reagent. Okay, but if you want something milder, then you use PCC. PCC is mild because it will only take the primary alcohol to the aldehyde, and of course it will take the secondary alcohol to the ketone. Okay, all right. Now, bariatric redox reactions, nature employs reducing and oxidizing agents. They are generally complex and selective. Why? Because they're complex and selective because, of course, they have a lot of specificity about them. And when you look at NADH, it's such one of those reducing agents. It is composed of many parts. It has a base, adenine. It has a sugar. It has a phosphate linkage and a sugar ribose, and also the reactive end center. And so this is where you have the hydride is transferred. See, this is the source of the hydride. It acts as a hydride delivery agent. Okay, it acts as a hydride delivery agent. You see, it acts as a hydride delivery agent. You see, and so these are things you want to remember. Okay, now this is one way that nature converts carbonyls to alcohols, right? See, because catalytic, you need an enzyme. Okay, and so the NAD plus can also, once the proton has been lost, right, it can also retrieve the proton again. All right, it can retrieve the proton again. It helps to, in this case, it helps to oxidize the alcohol to the corresponding ketone. See, so this helps. Now, this plays a role in so many things like secret